video, we're going to be talking about Stokes' theorem and Green's theorem. So these are sort of vector calculus versions of the fundamental theorem of calculus. And we're going to introduce these two theorems. And before we do that, let's review one way of looking at part of the fundamental theorem of calculus. It says if we're integrating a derivative, then we can find the definite integral by evaluating the antiderivative of the given derivative function at the boundary. Okay, and Stokes and Green's theorem are we're integrating a curl of a vector field. So a vector field, the curl of the vector field is a vector field, and the curl of the f is a type of derivative. And we're going to integrate that over a surface, do a flux integral or surface integral. And that's going to be equivalent to just integrating around the boundary. The boundary is going to be a curve, so that's going to be a line integral. Okay? And Green's theorem is just Stokes' theorem, but restricted to the surface being in a plane, and the curl is just the two-dimensional version of the curl, just the z component really of the curl vector. Okay, and so in the Green's theorem then, well actually in both of these theorems, one version is a surface integral, but it can be ultimately turned into a double integral using a parameterization. And the other version is a line integral, which can be turned into a single integral using a parameterization. So let's take a look at the actual statements. So Stokes' theorem says if S is a smooth oriented surface with a piecewise smooth oriented boundary curve C, and the direction around the curve matching the orientation of the surface, that is using the right-hand rule. So if you sort of put your fingers around the curve, that's the boundary curve of your right hand, then your thumb will point in the basic orientation of that surface. Okay, and then we're going to be integrating a vector function, vector field, f. It's a smooth vector field on the open region containing S and C. It's got to contain all of S and all of C, no holes in it. And what this turns out to be is if we do the surface integral over S of the curl of f dot dA, we do that surface integral, that's the same as integrating the line integral around the boundary curve of f dot dr. Green's theorem is the same thing for a plane. If R is an open region in a plane, that's our surface, but it's in a plane, and the boundary is a piecewise smooth simple closed curve C, with the direction around the curve so that the region is always to the left of C. And if you think about that, that will means that the direction, if we use the right-hand rule, the orientation of the surface is always pointed in the upward direction out of the plane. So if it's the XY plane, the orientation is pointed in the the positive Z direction. And let's see what else we got. F is a smooth vector field on the open region R, containing R and C. Again, no holes. Well, this integral curl dot dA in a two-dimensional setting, this surface integral is equivalent to this double integral over the region. That curl, the Z component of that curl is this right here, partial derivative of f of the second component of f with respect to x minus the partial derivative of the first component of f with respect to y. And then the other components, the x and y components of that curl are 0. So when we do that dot product, the only thing that's left is this piece and then your dA differential here. So this is a double integral. Of course, we're going to turn a curl or a surface integral into a double integral anyway, but this is basically already doing the double integral conversion, but it's the same integral as this up here really. And then we get the same result, that's equal to that line integral. So let's do an example of each. So here is an example of Green's theorem in action. So we're going to evaluate the line integral over a curve of a given field, and C is the circle centered at the origin of radius 4. F is the vector field negative y comma xy squared, and we're going to calculate it directly. Okay, so let me just point out real fast again. So these theorems here, they say that there are two different ways of getting the same thing. So if we have this expression on the right, we can write it as the one on the left. Or if we have the one on the left, we can write it as the one on the right. So we can go back and forth, and of course that allows us to choose whichever one of those is the easiest to do, and we can do the integral that way. Or if we do it both ways, that gives us a check of our work. Okay, so here's doing it directly, and that means we're going to have to parameterize everything in terms of a parameter t and turn the line integral into a single integral. Okay, so we need to parameterize the curve. The curve is a circle centered to the origin of radius 4. We've done this type of parameterization before. If we let basically t be theta, you've got r vector function of t is 4 cosine of t comma 4 sine of t, and let t run from 0 to 2 pi. Then r prime of t, let's see, the derivative of cosine is minus sine, and the derivative of sine is cosine, so the r prime of t becomes minus 4 sine of t comma 4 cosine of t. The vector function f that we're integrating is minus y comma x y squared, and to integrate that, or to continue on, we need to change that into a function of t. So the y's are replaced by sine of t. See, the y here and here are replaced by sine of t. That's here and here. And the 4 sine of t, excuse me. And the x's are replaced by 4 cosine of t. That's here and here. All right, let's simplify just a little bit. Not much we can do with the first part. Squaring 4 is 16 times 4 is 64. This is a sine square of t, and then we still have a cosine of t. So that's f. And if we do f dot dr, that's just this f dot this r prime times dt. Okay, and so we, of course, we still got a dt, but we're just doing that vector function dotted with that. Okay, well, that just means multiply the first parts plus multiply the second parts. So this is 16 sine squared t plus 256 sine squared of t cosine squared of t dt. And so that's what we're going to integrate with respect to t from 0 to 2t, which are the ranges, the interval for t values there. And so we've turned this line integral into a single integral. All right, let's see what we can do with this. Well, I see a lot of sine and cosines to even powers, so we're going to need to use our technique from Calculus 2 of using the trig identities to reduce the powers, the power reducing identity. And so the identities we're using are sine squared of t is 1/2 parentheses 1 minus cosine of 2t, and we're also going to use in a minute the 1/2 1 plus cosine of 2t is cosine squared of t. So this sine squared t replaces 1/2 times the 16 is 8, and then 1 minus cosine of 2t. This one also is 1 minus cosine of 2t. This is 1 plus cosine of 2t. They both have a half. That's a fourth. A fourth of 256 is 64. 1 plus, 1 plus, or a plus b times a minus b is a squared minus b squared. So 1 minus cosine t times 1 plus cosine t is 1 minus cosine squared t. Distribute to 64. We get 64 here. And then let's just start with that a minute. So that's a 64 there. And then you get 64 times this part. Okay, but this is going to be 1/2 1 plus cosine of 4t. So we're playing that double angle, half angle, power reducing identity, whichever way you want to call that identity. So that power reducing, I did it again. The 1/2 of the 64 and the negative there makes this negative 32. Distribute that, we get this. Now put all the constants together. 8 plus 64 minus 32. Well, 64 minus 32 is 32 plus 8 is 40. We still have that term. We still have that term. Okay, now we finally got it into a form where we can find an antiderivative pretty easily. This is 40 becomes 40t. Do a u is 2t, put a 1/2, make that negative 4, and the antiderivative cosine u is sine of u. Put that u be, or pick a different letter, w equals 4t here, dw is 4 dt, put a 1/4 there, makes that 6. Let's see, 1/4 of that should be not 16, but 8. Let's fix that. Okay, fix that there. So let's see, let's check it again. The derivative of this, the derivative of sine of 4t is cosine of 4t times derivative of 4t is 4 times the negative 8 is negative 13. Okay, that checks. Okay, evaluate from 0 to 2 pi. Take this, plug in 2 pi for all the t's, 0 for all the t's. And this is not going to affect the answer I had because 40 times 2 pi is 80 pi, but all the rest of these things are 0. That's sine of 4 pi is 0, sine of 8 pi is 0, 40 times 0 is 0, sine of 0 is 0, sine of 0 is 0. All these are 0. So you just get 80 pi, or approximately 251. Okay? Now that's doing this problem directly. Let's do it indirectly by using Green's theorem. If we're going to work this out indirectly, we do not have to parameterize things. Okay, we do need to find out a couple things. We need to find out this scalar version of the curl here. Okay, first of all, we got to make sure we can even use Green's theorem. The hypothesis of Green's theorem are satisfied. The circle is a simple closed curve, and it is going around the region that we want. Okay, and so the vector field there is defined everywhere in all of the region on the inside. So R is the interior of that circle. So C is the circle itself. That vector function is defined everywhere there. So no holes in that. So we can use Green's theorem. So let's go ahead and find this. This is the partial derivative with respect to x of the second part minus the partial derivative with respect to y of the first part. So let's see. When you do the derivative of this part with respect to x, you get y squared. Do the derivative of that part with respect to y, you get -1. That negative makes it plus. So get y squared plus 1. Okay, now since we're integrating, this is going to be a double integral. We're going to integrate y squared plus 1 dA. But the integration region is the interior of a circle. It's a circular disk. So it's going to make a lot more sense to set this up in polar coordinates because it makes the region really easy to do. So dA becomes r dr d theta. Remember that from integrating double integrals with polar coordinates. But by setting up that way, the r runs from 0 to 4 and the theta runs from 0 to 2 pi. So we have nice constant limits there. Now to do that, we're going to have to take the y squared plus 1 and write it in polar coordinates. But y is r sine of theta, so this is r squared sine squared theta plus 1. Okay, so distribute the r, that's r cubed sine squared theta plus r. Take an antiderivative with respect to r. That becomes r to the fourth times 1/4. This is treated as a constant. This goes up to power 2. Divided by the new power, it's 1/2 r squared. Evaluate from 0 to 4. So plug in a 4 for the r's here and here, and a 0 for the r's here and here. All right, so let's see what this turns out to be. 4 to the 4th divided by 4 is 4 to the 3rd, which is 64 sine squared theta. This is 16 divided by 2 is 8, and that's got a 0 there, and that's a 0. So the last part is 0. Integrating with respect to theta, well, this sine squared theta, we need to do a power reducing identity. It's 1/2 of, well, first of all, I factored an 8 out. That left this to be 1. 8 times 8 is 64. So this is an 8 here. But then the 1/2 from the identity brings that 8 down to a 4. And then you got 1 minus cosine of 2 theta. Distribute, we get 4 plus the 1 here is 5 minus 4 cosine of 2 theta. All right, now we can integrate that. That picks up a theta here. And turns this into a sine of 2 theta. So cosine of u, then du is 2d theta, so you put half of that, it makes this into 2, and you get cosine u becomes sine u here. So just check it by doing the derivative. The derivative of this is 5, the derivative of this sine of u is cosine u for the derivative, then we get 2, derivative inside is 2 times the minus 2 is -4, so that works out. Evaluate from 0 to pi, take this, put 2 pi in place, 0 to 2 pi, put 2 pi in place of the thetas, 0 in place of the thetas here. The first one is 10 pi, and all the rest of them are 0, and that becomes 80 pi. Okay, so that was 80 pi, and oh, we got 80 pi that way, right? So they're both works the same both ways. You can decide, I guess, whichever one you think is easier to work and work it that way, or you can do it both ways and check. But Green's theorem says, of course, that these two ways should give you the same answer. All right, let's do a 3D version. Let's do Stokes' theorem. So let's evaluate the flux integral of the curl of the given vector field over the given hemisphere, which is oriented in the positive y direction, and calculate this integral directly. So the surface is x squared plus y squared plus z squared equals 1. That's going to be a hemisphere with y is greater than or equal to 0. That's going to, the y greater than or equal to 0 cuts it in, so it's only a hemisphere, not a full sphere. And the vector field f is y, z, x. But we're not integrating vector field f, we're integrating the curl of f. So let's do this directly. So we need to find a couple of things. The first is we need to parameterize this surface. And I'm going to basically parameterize it using polar coordinates, right? So instead of calling the parameters, say, I think I've been calling them t and u, some people use s and t, I'm going to just use theta and phi. We can use any letter we want, but these are our normal meanings of theta and phi. So remember from polar coordinates, if we go out to a sphere, the x's are going to be sine of, where they're going to be, let's see, sine of phi cosine of theta is x, and with rho is 1 because we're on the sphere, right? So it's rho sine phi cosine phi, but rho is 1. Y is rho sine phi sine theta, but rho is 1. And z is rho cosine of phi, but rho is 1. So it works out to be this if we let theta run from, if theta runs from minus pi over 2 to pi over 2, we do get a, yeah, we get the correct half circle that we want, right? So you get, or half of the sphere. Okay, so that works out. And then phi runs from 0 to pi. Okay. Is this how we want it? Actually, no. We want the y's to be positive. Y's are positive. Theta going from 0 to pi, that should say. Okay, let's fix that. Okay, so theta runs from 0 to pi will give you positive y's. phi running from 0 to pi will give you the hemisphere. Okay. Now, we want to find, we need this cross product here in the in setting up the double integral to turn this into a double integral with parameterization. Okay, so we need to do the partial derivative of this function with respect to theta and with respect to phi. So with respect to theta, see, derivative cosine of theta is minus sine of theta. The sine of phi is treated as a constant. Derivative sine theta is cosine theta. That's constant. Derivative cosine of phi is treated as a constant with respect to theta, so that derivative is 0. Now we do the derivative with respect to phi. We get the derivative sine phi is cosine phi, so it's cosine phi cosine theta. The next term would be cosine phi sine theta, and the last one is minus sine of phi. Then we're going to do the cross product of these two things, these two vectors. And whoops, that's worked out here. Details are worked out, so you find the I component. So you write ijk there, write this one here and this one here. And so for the I component, you're multiplying these two minus these two. That was a 0, so that knocks out. So it's just these two multiplied together, minus sine square of phi cosine of theta. That's good. And then for the j component, get rid of that row and that column. So it's the middle one is backwards in sign. So you multiply these two, that's 0, minus these two, minus, and the other minus makes 3 minuses. So it's negative sine square of phi sine of theta. And then for the k component, we get rid of this and this. So we multiply these two minus these two. So multiply these two, we get minus sine of phi, cosine of phi, sine square of theta. And then minus here, multiply these two, you get a sine of phi, a cosine of phi, and a cosine square of theta. On these last two, notice they both have a minus sine phi cosine of theta. Cosine of phi, let me say it right. They both have a negative sine phi cosine phi. Factor that out, and you're left with sine square theta plus cosine square theta, which is 1. So that's how that simplifies there. All right, so we have that piece. We need that. And the vector field that we're integrating over is not this field, but rather the curl of that field. So let's find the curl of that field. And it's the way you do that, the curl is del dot f, so del cross f. So you set it up like this, and that is you take for the I component, you take the derivative with respect to y of x minus the derivative with respect to z of z. So that's 1, that's 0. So we have minus 0 minus 1 is negative 1 for the first part. For the j part, remember the signs are backwards, so we start this way. The derivative with respect to z of y minus the derivative with respect to x of x. This part is 0, that part's 1, so you get minus 1 in the middle. And for the k component, get rid of that row and column, do this part, determinant. So the derivative with respect to x of z minus the derivative with respect to y of y. This part is 1, and this part is 1, that's 0, 1 minus 1. All right, so there's our curl of the original function, and this constant function is the function that we're going to integrate over. Okay, we're going to find the flux of that vector function through this hemisphere. So now we need to do curl dot dA, which is the curl dotted with this. This thing right here, which we found on the previous page, d theta, d phi, in one order or the other. So pulling this from the previous page, we have this here, and then the curl is what we just came up with there. So that's normally it's just f dot dA, but the f that we're integrating is the curl of that f. All right, so multiply the first times first plus second times second plus third times third. 0 times the last part is 0, so that's not going to come into play. these two negatives multiply together to get positive, sine square cosine phi, and the negative here multiplies together to get sine square of phi sine of theta. They both have a sine square of phi, so I factor that out and then say it's sine square of phi times cosine theta sine theta. Now, the integral for the surface integral then is rewritten as a double integral with this parameterization in terms of phi and theta. And so let's see, we run, it looks like actually both phi and theta are running from 0 to pi. And we can do either order here. I chose to do the phi first. So the cosine theta and sine of theta are constants with respect to phi, so that can be pulled out front. And we're just integrating from 0 to pi sine square phi. We use our power reducing identity, 1/2, 1 minus cosine of 2 phi. And so an antiderivative there is, well, the half, we still got that half somewhere, so I pulled it all the way up front. Now the antiderivative of this part is a phi, and then we've got a minus 1/2 sine of 2 phi. Just a substitutionary u is 2 phi. Evaluate from 0 to pi. We still got our half, still got this function of theta here. But this part here, we put a pi here and here, minus put a 0 in both places. Well, that's pi. Sine of 2 pi is 0, that's 0. Sine of 0 is 0. So that's, all those are 0, so you just get pi right there. And so we have evaluated that first part of the inner integral to be just pi, which I brought out with the 1/2 to make pi over 2 out front. Now here, an antiderivative of cosine is sine, antiderivative of sine of theta is minus cosine of theta, and theta is going to run from 0 to pi. Plug in pi is here and here, 0 is here and here. Sine of pi is 0, cosine of pi is -1, and that negative makes +1. That sine of 0 is 0, cosine of 0 is 1, negative, and negative makes it +1, and 1 plus 1 is 2, times the 1/2 here cancels, leaving only the pi, which of course is about 3.14. Okay, so there's the direct way to do it. Now we can use Stokes' theorem to do the integral as well. So notice that the curve is we got it oriented the right way. The vector field is defined everywhere there. Both the curl and the original vector field defined everywhere there. So we can do it by just turning this into a line integral around the boundary. Okay, so the boundary curve is just a circle. Okay, it's a circle in the y has to be positive on this thing, but the boundary curve is in the xz plane. So the y is always 0. Okay, so this is 0 here, and then then it's just it's like we always parameterize a circle. X is cosine t, z is sine of t. If you're doing a circle like the unit circle in the xz plane. So when you do r prime of that, you get minus sine of t, 0 cosine of t. Our f of xy is y, z, x. We can get it in terms of our parameter t. The y is 0, so that's easy. The z is going to be sine of t, and the x is going to be cosine t. So substitute those in. Then you do f dot dr. It's just this f dot this r prime with the dt. And let's see, 0 times this is 0. Sine t times 0 here is 0. Cosine t times cosine t is cosine squared t. So you just get cosine squared of t dt, and we got a much easier integral to work out here. This line integral, first of all, it's just a single integral instead of a double integral, and secondly, it's pretty straightforward. It does use this power reducing identity. Cosine squared of t is 1/2, 1 plus cosine of 2t, and we're going to integrate from t going from 0 to, I should say, going from 0 to 2 pi. Okay, and well, let's see. An antiderivative of, let's see, the 1/2 we brought up front. The antiderivative of 1 was just t. The antiderivative of cosine of 2t is 1/2 sine of 2t. And you're going to go from 0 to 2 pi. So plug in the 2 pi here and there, 0 here and here. This is 2 pi. This is sine of 4 pi, which is 0. That's 0. Sine of 0, that's 0. So this is 2 pi times a half is pi, once again. So we get pi either way. In this case, I would say that this page here, is much simpler than what it took for those 2 pages to get the same answer. So we've seen an example of Stokes' theorem and Green's theorem. We've shown, we've illustrated that it works at least for those particular examples, and that it works in general if the hypothesis of these theorems are satisfied. And so you can see how you can use Stokes' theorem or Green's theorem to somehow rewrite one integral in a different form, and perhaps get a much easier problem solved that way.